Okay, lecture problems for chapter 12. Take a second to read the problem. You can see I already have my pretty picture here. So the sailor is going to strike his boat. The sound wave is going to go down. It's going to come back up. And we know that the time for that round trip is going to be 2 seconds. And I'm interested in solving for the distance to the bottom. That's going to be the speed of sound in water multiplied by the time. Need to be very careful here and say I'm only interested in the depth, so I'm only interested in the time down to the bottom, not the round trip time. So the time I'm interested in is actually going to be half of 2 seconds, or 1 second. I can look up the speed of sound in water, 1560 meters per second. So the depth is simply going to be 1560 meters per second multiplied by 1 second. The distance will then be 1560 meters, which is just under a mile. Something that is not true is the speed of sound in seawater is not going to be a constant varying with depth. That's one of the reasons why they're having such a hard time finding that Malaysian flight, is because the speed of sound is different in water as the depth goes down and temperature changes. Okay, take a second to read number 12. I'm given the sound level for 4 engines to be 140 decibels. Plane engines are very loud, by the way. And I'm interested in the sound level for 1 engine, and I'm giving a hint to add the intensities, not the decibels, not the sound levels. So what I do is I page back and I look at examples 12.4 and 12.5, and that shows me an example of this, so I'll pretty much follow it straight out. I know that the intensity from 1 engine is going to be a quarter the intensity from 4 engines, so adding the intensities, or in this case subtracting the intensities. And my sound level is going to be then 10 log this intensity of 1 engine divided by my intensity threshold. That's going to now give me 10 log of 0.25, the intensity from 4 engines relative to the sound level. And now I can go ahead and I can write this as 10 log of 0.25 using the rules for logs, plus 10 log of the intensity of 4 engines relative to I naught. This guy right here is simply this right here, so 140 decibels. Take the log of a number less than 1, you're going to get a negative number, so you pack that in, you get -6 decibels, and thus the sound level is going to be 134 decibels. For number 28, I have an organ pipe that's going to be 1.16 meters long, and I'm looking for the fundamental frequency as well as the first 3 audible overtones for, in part A, a closed pipe. So looking through the book, I find a tube closed at one end, and I can figure out the fundamental, and then it's only going to have odd harmonics, so 1, 3, 5, 7, 9, so on and so forth. So first, the fundamental is going to be the speed of sound divided by 4 times the length of the pipe, so 343 meters per second divided by 4 times the length, which is 1.16 meters, and I'm going to come up with 73.9 hertz. Now I'm looking for the next 3 overtones, which are all going to be the odd ones. So starting with 3, it's going to be 3 times the fundamental frequency, kind of right here. So 3 times 73.9 is going to give you 221.7 hertz. the fifth harmonic, it's going to be 5 times the fundamental, which is going to be 396.6 hertz. And lastly, the seventh harmonic, the third audible overtone, 7 times the first harmonic multiplied by 7. That's going to be 517.4 hertz. So overall, not too bad. Now moving on to part B. Now the pipe is going to be open at both ends, so I can find an expression for the tube that's going to be open at both ends. Note that it's going to have all of the harmonics, not just the odd ones. So I can first find the fundamental, which is going to be the speed of sound in air divided by 2 times the length, so 343 meters per second, 2 times 1.16. Go ahead and I type all that in, and I get 147.8 hertz. Now I'm going to have all of the not just the odd harmonics, I have all of the odd plus the even harmonics. So the first overtone is going to be the 2 times the initial frequency, which is going to be 295.7 hertz. Now the third harmonic will be 3 times the fundamental frequency, which is going to be 443.5 hertz. And lastly, the fourth harmonic, so 4 times the fundamental, put that one right there, is going to give me 591.3 hertz. Number 46, take a second to read it. A piano tuner is going to hear 1 beat every 2 seconds, so we know that the beat period is 2 seconds, and the frequency of one of the strings is 350 hertz, and I want to know how far off the other string is in frequency. I know that the frequency is related to the period, simply the inverse, so that tells me that my beat frequency is 0.5 hertz, and this simply is how far off in frequency the 2 piano strings are. We don't know which direction, so it could actually be plus or minus 0.5 hertz. So that's actually the real answer. Number 57, we have a bat putting out a frequency of 50 kilohertz, and we have an object moving away at 27.5 meters per second. So the first thing I do is I'm following essentially example 12.16 in the book, where there's 2 Doppler shifts, and it even says, hey, this is how bats do it. So the frequency received by the object will be equal to the frequency of the bat multiplied by 1 minus the speed of the object divided by the speed of sound. Let's call it Vs from now on. The reason why it's a minus is because the object is moving directly away from the bat. That's why we're using one with a minus sign here. And then we're going to have the frequency received back by the bat. I'll put a double prime on that to indicate that. That's going to be the frequency emitted by the object, divided now by 1 plus the speed of the object divided by the speed of sound. So that's going to be equal to then the frequency, or the initial frequency of the bat, 1 minus v of the object divided by the speed of sound. Divide all that by 1 plus velocity of the object, velocity of sound. You could just go ahead and plug everything in right now, or you can do just a little bit more algebra and get the frequency of the bat to be the initial frequency of the bat multiplied by velocity of sound minus velocity of the object divided by the velocity of sound plus the velocity of the object. Essentially all I did was I multiplied the top and the bottom by the speed of sound. And lastly, I get to plug everything in. So 50 kilohertz, I'm leaving the units in there for a bit. 343 meters per second is the speed of sound. The speed of the object is going to be 27. And then down here I'm going to have 343 plus 27. And I peck all that into my calculator and I come up with 420, scratch that, I come up with 42.7 kilohertz.